Hi, William. I just want to send you this video with all of your questions in kind of one place. I feel really bad that we missed your questions. My apologies. I was not even on my radar that there might be an issue with where the student questions went. Like I said on my math lab, it went directly to my email, and I just assumed WebAssign would do the same thing, and it really caught me off guard when it didn't, and I didn't have any of that instruction in the instructor information from the beginning of the course. So I'm going to give that feedback back to the course developers, because I really feel like they should be better preparing instructors who have not taught under this particular course before, because it's really different from the other courses at Embry-Riddle. So I will give that feedback, and I'm really sorry that I missed your questions, and I just want to put that out there first. I'm also going to just review what I sent you in case my email didn't make sense. I sent you something back last night just because I wanted to get you something, but I didn't really send you back a lot of the theory that went with it. I gave you kind of how to get the answer, but I wanted to make sure you understood where the answer was coming from. So I'm not going to necessarily go through the pieces, because I gave you an example from the textbook that you could use for the wording. My concern is that WebAssign is looking for a specific method of answering, and I don't want to deviate from that method of answering, because I don't know how else it'll know to grade you. Like, I don't know if it's looking for certain words to grade you. I don't know how a computer can grade a proof. But with that, that's why I was a little worried about making sure I gave you the exact wording that you should use to get there. To give you an example, if I was teaching this, my instruction would be to make a continuity statement first, because in both of these theorems we have this this important statement of continuity. F of x is continuous. F of x is continuous. And so my first instruction would be to make a continuity statement, but that's not what they did in the proof that I read within WebAssign. So just follow their examples, and if you still have trouble getting the quote-unquote right answer, let me know and we can see if we can't problem solve that. But let me tell you exactly what they're talking about. IVT is that given a function f of x is continuous, I think I lost the is continuous on x as a to b, such that f of a is less than 0, f of b is more than 0, or flipped, then there exists some c between a and b such that f of c is equal to 0. So what they're saying is, if you have a continuous function between two x values, it doesn't have to be continuous everywhere, but it has to be continuous where we're worried about it. And one of the y values is negative and one of the y values is positive. It can go negative positive, or it can go positive negative. It doesn't matter, but it just has to be so they're separated by negative and positive. Provided that it is continuous, then somewhere between a and b there's a c such that f of c is actually equal to 0. So IVT is simply stating that you've got this function across the x-axis, and f of b is positive, or f of a is negative, or flipped. Okay, so just we have an f of a or f of b, that one side's negative, one side's positive. Provided that the function is continuous, the only way you can go from a negative to a positive, or a positive to the negative, is if you hit a 0 in the middle, provided that it's continuous. Now, if it's not continuous, you could jump over 0, which is why we have to have that continuity statement. But you can't go from negative to positive or positive to negative without a 0. And then Rolle's theorem states that if you have an f of a and an f of b that are equivalent, the only way that could happen is if somewhere, and it can be more than once, somewhere we need to have a horizontal tangent line. Somewhere between f of a and f of b, there has to be at least one f of prime equal to 0. That's the only way. Now, it could be a straight line so that all of f of prime is 0, I suppose. But somewhere you have to have at least one place where f prime is going to be 0. So in between f of a and f of b, provided f of a and f of b are equal, then you're going to have an f prime of c that's equal to 0. If you don't have an f prime of c that's equal to 0, then that also means that you can never have the f of a and f of b equal. That means there won't be any repeating points, because the function never swoops back around. So what the proof wants you to do is state that it's continuous, and we know that because 8x is continuous and cosine of x is continuous. So summed together, they're going to stay continuous, because there's no opportunity for you to lose a graph to an asymptote or a negative square root or anything like that. So all we have to do to show that 8x plus cosine y, or 8x cosine x, equals y, can ever equal 0, is by taking this and showing that there's an x, any x, literally any x, that will make this negative, and literally any x that will make this positive. I think really easy, that you don't win any points for picking weird x values. So think about what will make this positive and put them together. And this negative, so this will be negative, right? And put them together. So literally any value so that it will make this negative, and any value so that it'll make it positive. And somewhere between those two x values, there must exist another c that will make this 0 if you can prove that. So that's your first step. And that's how you prove IVT. But you have to prove that there's not another place that this could be 0. So that's where we need roles, because we need to prove that the function's never going to turn around, which means we need to prove that 8 minus sine of x equals y can never be 0. And that's true because if you solve this algebraically, you get that. And that's a contradiction because sine, by its normal range, is between -1 and 1, so it can't ever equal 8. So because it can't ever equal 8, that means this cannot be true, and that means we never have an opportunity for the function to swoop back around. So if you can prove that this is true for some c, then that would be the only real root, because the function never swoops back around. So that's how you use those two. Like I said, go ahead and go back to the other information to see if you can't get the wording in such a way that the homework system will grade you appropriately. Because again, I don't know how a robot would grade that. All right, so next question. You just had a question about how to get that log. That's just some pre-calc stuff. They just want you to use algebra to solve this. So the one complaint I have with this is they want you to use log base 2, which I almost never use because my calculator does not have a log base 2, but it is the more efficient way to cancel out the log, so to speak. So what they wanted you to do was do divide it by 10, so you get 1 over 10. And then we use log base 2 on both sides. And then, because logs and exponentials are inverse operations, the log base 2 and the 2 cancels each other out. And we're ending up with log base 2 of 1 over 10 equals negative t over 30. So that t is negative 30 log base 2 of 1 over 10. And again, that's just college algebra level stuff. So that's where those steps came from. Now, to be fair, I would have taught it differently if I was in class. I would have used natural logarithms. And maybe that's what you meant when you said you didn't do it. Because when you use natural logarithms, you use a change of base. So that negative t over 30 would come down, and I'd end up with negative t over 30 equals ln of 1 over 10 over ln of 2. And that would be a change of base, and then I would get that t is actually equal to negative 30 times ln of 1 over 10 ln of 2. Perhaps that's what you meant when you said you didn't use that, but that's what they were getting at there. They wanted you to use the log base 2, which is a valid way, but again, I don't have log base 2 on my calculator, so I would have solved it out like this, but that's what they're prompting for. This one was from a while ago, and I think someone asked this in a discussion. I remember talking about it in a discussion, but this is the greatest integer function. Calculus textbooks love greatest integer function because it's one of the only functions that we have that gives us a really good jump discontinuity. Piecewise, it looks like a piecewise function where you have, it kind of looks like this. This graph is incomplete. That's why it wasn't there. But that's what that looks like. So greatest integer function, and they list it here. Okay, and it has these jumps. We call it the greatest integer function. It also means the greatest integer you have is how I explain it. So like 1.3, the greatest integer that you have is, the greatest integer that you have at 1.3 is 1. right? The greatest integer you have at 0.75 is 0. You have no full integers if you're at 0.75. And then it works backwards sort of in the negatives. If you have negative 1.3, negative 1 is greater than that. So you wouldn't have negative 1, you'd have negative 2, right? So it works backwards. It's the most amount of value that you have. So you can also think of it as a round down function. That's what my calculus students in person like to usually call it, as a round down. And so the reason this answer is going to be integers here is because at every integer, you have a jump discontinuity, and so it's not differentiable there. It's not differentiable. But it is differentiable at all the space in between the integers because it's continuous. Since it's discontinuous there, it's not differentiable at 0, 1, 2, 3, 4, or negative. Okay, so that's why it's not differentiable at the integers. And that's why where it is differentiable, the derivative is 0 because it's a flat line. And that would be the way you'd graph it. Okay, so again, this is a long time ago, but I just want to make sure I answer all of them. I went through and took screenshots of all your questions. The limit exists here because there is a removable discontinuity. So the thing I really like to tell students is to very first start by subbing this in. If you sub this in, you get 144 plus 25, which is 169. So if I sub in, I get the square root of 169 minus 13 over 12, negative 12 plus 12. And then that's going to be 13 minus 13, which is 0, and negative 12 plus 12, which is 0. So I get 0 over 0. This insinuates a discontinuity because 0 is in the bottom. But when you get 0 over 0, we call that indeterminate. Call that indeterminate. And that literally means not able to be determined. It is a fuzzy, ambiguous answer that we don't really have quantity for. Like, what is infinity divided by infinity? That's another indeterminate form because it doesn't mean anything. Boundlessness divided by boundlessness is 1. Well, what if the boundless sizes are different, right? So we can't quantify it because we don't know what 0 divided by 0 is. You're taking a pile of nothing and putting it into absolutely no groups. What is that? You know, it has no value. Is it 0 or is it undefined? We don't know. And so when you get these, this is what indicates we have something called a removable discontinuity. And a removable discontinuity is one of those things where the function is technically discontinuous. There's a hole. But that hole is a space where the function doesn't exist, but the limit, because it approaches the same point, does. So the way I would solve this algebraically is I would take the x plus 25 minus 13 over x plus 12. And when I see these, I immediately think, oh, we need to rationalize the denominator by, or numerator by adding the conjugate or multiplying by the conjugate. So this would be x squared plus 25 plus 13 times x squared plus 25 plus 13. And when I get there, I multiply these two sides together, and I end up with x squared plus 25 minus 13 squared. And then I end up with x plus 12. And I end up with x squared plus 25 plus 13, excuse me. And so when I algebraically manipulate that, this ends up being 169. I don't have my calculator here, but 169 minus 25 is 144. Okay, which is good because that's going to be how we get rid of that 12. So then this ends up being x squared minus 144 over x plus 12 times x squared plus 25 plus 13. And then x squared minus 144 is x plus 12 times x minus 12. And I get rid of the plus 12s. And I end up with x minus 12 over x squared plus 25, square root of plus 13. So what I've done now is I have removed the removable discontinuity. When I divided out this piece, I kind of divided out that piece that's making that whole, which will allow me to assess the limit more effectively. So now when I find the limit as x goes to negative 12, I can find it at x minus 12 all over the square root of x squared plus 25 plus 13. And when I plug it in, I get negative 24, excuse me, I almost called it 144, negative 24. And then negative 12 is 144 plus 25 is 169. Square root of 169 is 13. 13 plus 13 is 26. And when I divide by 2, I get negative 12 over 13, which is what the answer was. So again, what you do is you plug in that value. When you get 0 over 0, that indicates an indeterminate form. That's probably a whole. If it was just 0 on the bottom and a number up here, that would indicate an asymptote. But since it's 0 over 0, that indeterminate nature leads me to think it's a whole. So algebraically, I rationalize the numerator, and I do that because anytime they add a radical in here, that's usually the cue that they're trying to give you is to rationalize. So I rationalize the numerator, and I put those together, and I ended up getting that. And once I got there, I was able to factor and cancel and all that good stuff. And then when I was able to divide out that piece, that removed the thing that was making it 0 over 0 or indeterminate, because that plus 12, if you plug negative 12 in there, you end up getting 0 over 0. So those factors are what was causing my indeterminate form. And then when I divided them out, I was able to plug in, and then I was able to assess the limit with that removable discontinuity eliminated. I think this is the last one. Phew. Okay, so with this one, the only thing you did wrong was they wanted you to do the g of x and f of u. So they wanted you to find the inner and the outer, and this is a weird notation. So you actually went ahead and, oh, I see. You put that inside, and they wanted it to be an f of u. See, x versus u, that should be u. And this guy, first of all, where is this in the book? Do you see that 3-5? That's your big help. So I went to 3-5, and I couldn't find an example exactly like this. The closest thing I could find was example 1, and that was a circle and not a hyperbola, but it's the same idea. The difference between a circle and a hyperbola is that it is x squared plus y squared equals radius squared. And then if you divide out the radius, you end up getting something similar to an ellipse if you divide out the radius on both sides, but only then both x and y are divided by the same radius, so it ends up being an equivalent statement. So a circle is that x squared plus y squared equals 1 over r squared over r squared. These are identical statements, but it's this nature of x and y having a common thing on the bottom. That's what makes it circular. The moment you flip it to be x squared plus y squared equals 1 over a squared plus b squared, this is what makes it an ellipse. Because now those are, oh, I shouldn't have put plus, my bad. I'm sorry, got a little overzealous. Right there. But that difference is what makes it an ellipse instead of a circle, because the radius is the same. And then if you put it, so ellipses are the like egg shapes, and circles are, perfect. Okay, so what makes it a hyperbola is when you add a subtraction sign. And that's because the moment you implement a negative, you end up having irrationality, or not irrational, imaginary, that's what I was looking for. And so that's what makes the hyperbolas of that shape. So A and B are just constants, and you were just supposed to know that because they define it as a hyperbola. And that again comes from like college algebra level material. and they just wanted you to find the derivative. And so you're just pretending a is a number. So that's 2x over a squared dx by dt, or yeah, dx by dx, which we don't need that necessary derivative, minus 2y over b squared equals 0. Don't forget the y prime. And then you end up with negative 2y over b squared y prime equals negative 2x over a squared. Can divide out the negatives. So that y prime is going to be 2x over a squared times the reciprocal of this guy. So b squared over 2y. Divide out the 2, and that is b squared x over a squared y, which is the derivative. So now we can use that to find the point at x naught, y naught, which is just some point, arbitrary point. Okay, so I like to use point slope. Y2 minus y1 equals m times x2 minus x1. This is going to be my m. My x, it looks like they put it in the x1 spot. Y1 is going to be x naught, y naught by their statement. So I call it y minus y naught equals b squared x over a squared y times x minus x naught. And so y is going to be b, x naught. I spoke too soon. Oh, wait, you did that. Now that I look at it, no, I kind of, I see, you just used the b squared, a squared. So I should have called it x naught, y naught there, excuse me, because those are the points we're using, so we plug that into the derivative. And so b squared x naught over a squared y naught is x minus x naught plus y naught. So you had very close to the same answer, you just forgot to plug, and to be fair, I did too, forgot to plug in the x naught and the y naught there at first. And that is because that's the point at which we're doing the tangent line, so you had to plug the x naught and the y naught into there at first to be able to say that's the slope that's happening at this point. Okay, if I need to go slower or repeat or anything, any of these, I ran through these because some of these I figured were older questions. I'm more than happy to do it again. I just email me and I will be happy to go back over anything.